Now that we've had a chance to talk about the change of basis problem and some orthonormal bases here. So at the end of last activity, we picked a vector, and then we had this orthonormal basis B and this other orthonormal basis B prime. Okay, we were able to convert the coordinates of the vector -2, 3 with respect to the ij basis into the B basis and into the B prime basis, and we found our transition matrices as well. Now, what's important about this is let's take a look at these transition matrices. I want you to list as many special characteristics as you can for each of these transition matrices. So we'll give you a minute to do that while we pause the video. Now that you've had a chance to look at those P and Q matrices, hopefully you notice that the rows of Q are orthogonal, and so are the columns of Q. And since P and Q are inverses of each other and they're also transposes of each other, the rows of Q are the columns of P and vice versa. So the rows are orthogonal, the columns are orthogonal, and as an added bonus, if you take the magnitude of the rows as vectors or the magnitude of the columns as vectors, you'll see that they're each length 1. And another cool thing that happened when we transitioned from one orthonormal basis to another orthonormal basis is that our transition matrix, either transition matrix has a determinant of 1 in this case. So let's go ahead and see something else that's pretty spiffy. So let's find the magnitude of vector W. Since there's no other special inner product given, we're going to use the standard Euclidean inner product, aka dot product. And so we'll get the square root of -2 squared plus 3 squared, which is 4 plus 9, which is the square root of 13. Okay. Now, if I take the W vector and I do his coordinates with respect to the B basis, and then I multiply that by the Q matrix, that's going to transition him from the B basis coordinates to B prime basis coordinates. So this is asking us to find the magnitude of the vector 2.32, 2.76, which, using our inner products here, 2.32 squared plus 2.76 squared, which amazingly is equal to exactly the square root of 13. Okay, let me slide this up a little more. Okay. What about if we take the W vector and we write him with respect to his B prime coordinates, and then we use the P matrix to multiply on the left to convert those B prime coordinates back to B coordinates. So now we're finding the magnitude of the vector 1.2, 3.4, which would be the square root of 1.2 squared plus 3.4 squared, which, oddly enough, comes out to be square root of 13 again. So what did you notice about the magnitude of the vector or the magnitude of the vector in either coordinate system? Well, they're all the same length. We're all the same magnitude here. Okay, that's pretty cool. So this transition matrix will preserve length. So will this one, because anything we do, if we take and multiply him, he will give us the same length as what we had originally. All right. So let's go ahead and try another basis. Now let's kick it up to 3-dimensional stuff. So let's let U1 be 4/5, -9 25ths, 12 25ths. U2 be 0 4/5, 3/5, and U3 be -3/5, -12 25ths, and 16 25ths. And let's take a quick look here. Let's do an inner product. So there's 0 minus 36 25ths plus 36 25ths. Aha! So those are orthogonal. -12 25ths Okay, plus 108 625ths, and plus that, and we will get 0 there as well. Let me just show you that on a calculator here. Okay, so I just typed it all in, and you can see that if I do my inner product, I left the parentheses off because I'm using order of operations, but U1 and U3 are orthogonal. Similarly, you can show that 0 minus 48 1/25ths plus 48 1/25ths is 0 again. And you can double check that each of these vectors has length 1. So this is an orthonormal basis in R3. Okay, probably not too surprising, but we have another orthonormal basis over here. Okay, and I'm going to pause the video and let you practice finding the transition matrix. Let's go from B to B prime. Okay, we'll pause the video and let you do that.